continue. Should have said this meeting is being recorded. I didn't hear it say that on my side, so hopefully it said it on yours. So welcome, my name is Dr. David Irvin. I'll be lecturing to you today for our Chemistry 2350 Survey Organic Chemistry. So what you should have seen is I have a separate YouTube channel aside just for our lectures. And so those you'll be able to go to YouTube and let me go to my channel and see if I can't my channel and show you that I'm going to share my screen real quick and share my screen with Google Chrome. Here we go. So what you should see is the organic chemistry channel here. And so the two most important channels for you are going to be this Incarnate Word channel, which has just our lectures, our recorded lectures and the hand notations and the questions and answers we give. Okay, so you can find all of those on here. And then of course there's the Introduction to Organic Chemistry, which has all of the pre-recorded videos for all the slides that we'll be going over this year. So if you missed something or you want to get see something again, those are broken up into smaller little bits and pieces. So you can see those. So if we look at playlists here, I have multiple playlists, but you have your own playlist here. It's UIW Chem 2350, and that's just these lecture classes, okay? And then this is for everybody who's taking my Introduction to Organic Chemistry with Brown and Poon stuff. So any questions about YouTube?
No.
No.
Okay, great. All right, I'm gonna stop sharing then. There we go. And what I'm going to do now is go over some of the stuff. Okay, so hopefully you've all been able to join up into Top Hat and look at the slides that are now aligned with our slides, and that you have seen that the homework is available to you. Right now, I have Chapter 1 homework due on Friday at midnight. So after today's lecture, you should have all the information you need to do all of the homework for that particular chapter. If you're having trouble with Top Hat, go ahead and email me, and we can see how to figure out that problem, what that problem might be. Okay. So, so you have two playlists on YouTube, both videos and our individual lectures. You have hopefully gotten a copy, either a digital or a physical copy of the book Brown and Poon. And you are starting to get Top Hat kind of working. On Monday, I'll send out another email with a new invite for this Zoom meeting. I was told that there might be a way for me to actually put the Zoom link on Blackboard. And so what I will try to do is figure out how to put the Zoom link on Blackboard. So you might be able to just go into the Blackboard and just click on the link and come into class that way. But I haven't figured that out yet, so give me a couple days on that one. But so you will receive an email on Monday with the link in it anyway, even if I don't figure out how to do it on that. All right, so that's what I consider all of my administration. Does anybody have any questions about the administration or availability of the books or anything like that?
No, it's clear.
Okay, great. So what I'm going to do now is I'm going to go ahead and share my iPad here and try to see if we can't pick up where we left off. Okay. There we go. I think this is where we left off. And I have my screen over here. So again, I have my participants set up. You can raise your hand or just mute. There's not very many of us, so you can just unmute and ask questions. I also have the group chat open, and so please feel free to ask questions at any time while we're going through this. Okay, so this is where we stopped last time. We were talking about Lewis dot structures of simple structures and how we would use those, the idea that we would try to put the atom that's going to bond the most in the middle, and then start building everything out from that, and then counting all of the electrons. Let's see, where did my stylus go? Oh, there it is. Flew across the room. Cat must have been in here. Okay. So we're going to extend on that, and then we're going to talk about the shape of the molecular orbitals, right? We have. So when we do the same, we can build these structures off of anything. And notice when we look at these, we like to put the carbons as part of the central molecule first because they tend to bond the most. And so when we start with our Lewis dot structures for our multiple carbon compounds, we still want to meet that requirement of having carbon have 8 electrons around it. And since each of these lines counts as 2 electrons, we have a total of 6 electrons here and 2 more electrons here. So that carbon is satisfied, and the other carbon has the same number of electrons surrounding it. And so what we'll see time and time again is we'll want to see either 4 bonds to carbon or 3 bonds to carbon and some kind of lone pair on it. Although that's very rare in carbon. So most of the time what we're going to do is we're going to see 4 bonds to carbon. It can be a double bond, a triple bond, or 4 single bonds. So to go along that theory here, we're going to have 1 bond here, 1 bond here, and 2 bonds here. So that's a perfectly full valence shell for carbon. Now, it doesn't have to be a double bond to carbon or even a triple bond to carbon. We can do other atoms too. For example, here we have a double bond to oxygen, and in the functional group nitrile, which we'll get into in the carboxylic acids chapter, we actually have a carbon triple bond to nitrogen. Okay. So all we have to do is, again, make sure we have that valence number of electrons in our system. In fact, to make sure our nitrogen has that right number of valence electrons, you'll have to put a lone pair out there. Okay, so now that we have the way to build our Lewis dot structures, let's move on to the general rules we want to always follow when we have this. Okay. So most of the time we're going to have neutral molecules, or we're going to have a charged species. If we have a charged species, we typically want to put it a negative charge on the more electronegative atoms like nitrogen or oxygen. And if we have a positive charge, we put that on the more electropositive or less electronegative atom like carbon. But for neutral species that contain either carbon, hydrogen, nitrogen, or oxygen, or halogen, and so that could be fluorine, chlorine, bromine, or iodine. The halogen and hydrogen always get 1 bond. So the hydrogen has 1 bond and no lone pairs. Okay, so just that 1 bond is the 2 electrons it needs to satisfy its rule. Carbon will always have 4 bonds and no unshared electrons in all the Lewis dot structures we'll be drawing in this class. Okay, there are rare occurrences, but we're not going to talk about those. Nitrogen will always have 3 bonds plus 1 lone pair. Oxygen always has 2 bonds and 2 lone pairs. And a halogen will have 1 bond like hydrogen. However, it'll also have 3 lone pairs available to it. And so we'll see these rules follow almost every compound we're ever going to write in our system for these neutral systems. So, okay. So this kind of sums up the last of the Lewis dot structures, and we can move on to formal charge. Okay, so once we've drawn our species, okay, and we've drawn it such that the Lewis dot structure is correct for that molecule or ion, now we have to figure out, is there a charge on that molecule? Okay, so if the molecule is neutral, we should end up with a 0 net charge, meaning there might be a plus on one side and a negative on the other, but the net charge on the whole molecule is 0. But sometimes, like in the case of the carbonate ion, we actually have 4 atoms making up something that has 2 negative charges. Okay, so the way we assign this, the way we figure this out, is by assigning formal charge to each and every atom in a system. And that starts with drawing a correct Lewis dot structure. Okay, so each atom has to be have all of its shared and unshared electrons. We have to show all the lone pairs. Okay, Now we have to think about how many electrons the atom had as a neutral solitary atom. So for example, carbon is in that group 4A, so it had 4 valence electrons to play with. Nitrogen is group 5A, so it had 5 valence electrons to play with. Okay, so that's one number we have to understand first, okay? And then we start comparing how many of the electrons are shared and how many of the electrons are not shared. Okay, so we have an equation associated with this. It's a very simple equation, but it's a very important one, where our formal charge is equal to the number of valence electrons of that neutral unbonded atom. So this is that A number that's on the top of the periodic table. So for carbon, it's equal to 4, okay? Then we subtract from that all unshared electrons. So these are lone pairs. Think of these as lone pairs. Okay, so so when we have things like fluorine or chlorine or oxygen, we're going to have lone pairs there, and we need to keep track of those. And then we have to do 1/2 of the shared electrons. Okay, why 1/2? Well, we're sharing that electron. It only has one of those electrons 100% of the time. It shares it the rest of the time. So we can only count half of a bond of those 2 electrons in a bond. So we call that the 1/2 of all shared electrons. Okay, so let's drew that for a couple different species here. Okay, so the first thing we're going to do is we're going to use those 2 different functions, drawing the correct Lewis-Dot structure and then assigning formal charge. And we're going to look at a few of these different species, and then you can do the rest of them yourself to make sure you have it. But let's do the first one here. Let's do A. Okay, oh, not that. There we go. And so we're going to start with this. And so if we're looking at this, we don't have a carbon. So we're going to think that, okay, nitrogen is our next most electronegative atom. And so it's going to probably be the one in the middle because it's going to be the one bonding more than one time. The hydrogens only bond once. So let's put our nitrogen in the middle right here. And we're going to put 4 hydrogens around it. 1, 2, 3, 4, because that's what our structure says we have. And now we have to figure out where that positive charge goes. Okay, so we do this by assigning formal charge to each of the atoms. Okay, so let's look at this. So let's remember formal charge is equal to the number of valence electrons the atom had neutral minus the lone pair electrons, or I'm going to do LP here for lone pair, plus 1/2 of the bonded electrons. Okay, so let's just do an example for hydrogen right here. Okay, so our formal charge on hydrogen is going to equal the number of valence electrons it brought as a neutral species. And for hydrogen, that was 1. So we're going to put 1 here. And then we're going to subtract from that the number of unpaired electrons, which is 0. And then 1/2 of the bonded electrons. And it has 2 electrons here. So there's 2 electrons, and multiply that by 1/2. And we're going to end up with 1. So our formal charge at hydrogen is 1 minus 1, which is equal to 0. Okay, so that means that hydrogen is not where this positive charge is. Okay, and we can do that same calculation for the other 3 hydrogens, and we're going to end up with all of those hydrogens having a net charge of 0. Okay, well, to make sure that we're doing this right, let's go ahead and do the same calculation for nitrogen. Okay, so we're going to do that same calculation where we have the formal charge is going to be equal to the valence electrons the nitrogen had as a neutral species. Okay, so we're going to move over to red here. So formal charge is equal to nitrogen right here is in the 5A group, which means it had 5 valence electrons that it brought to the party. So we're going to start with 5 here. We're going to subtract from that all the lone pair electrons, okay? We get to use all the lone pair electrons because those are actually on the atom. We have no lone pair electrons because we have 8 electrons around nitrogen here, and we don't have any lone pairs, so that's going to be 0 for this as well, minus 1/2 of the bonding electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8 bonding electrons, 8 right here. And so when we multiply 8 times 1/2, that's going to be equal to 4. And we have 0 for non-bonding. So we have 4 minus 5 is equal to a formal charge of +1. That means that the positive charge we see in this structure here is actually on the nitrogen, okay? Because it had a lone pair that it's sharing an electron with that last hydrogen, and therefore it gains a charge. It has fewer electrons on it than it has protons, therefore it has that positive charge, okay? So, does that feel like it's going to work out for? Yeah. Does that feel like we're, really understanding this? Let's do one that's a little more complex. I always want to do 3 of these examples so you get to really kind of figure out where the electrons are and everything like that. So, okay, let's do another one. Let's do this one right here. Okay, so we have NO2 plus. All right, so we're going to have a nitrogen here, and I think we're going to bond the oxygens to them right here. And oxygen had 6 electrons in it, and nitrogen had 5 electrons in it, and oxygen had 6 electrons in it right here. Okay, so let's see, what are we going to do here to make this a valid Lewis dot structure? We're going to lose one of these electrons because we have a positive charge. So now we have 1 fewer electrons than we needed. Now let's try to pair up all of our bonding ones. Okay, so we need to pair up these electrons here because we had a single electron here and a single electron here. So that gives us another double bond between those species. But we have a problem. The problem is that our oxygen here now only has 6 electrons around it if you count these. I'm sorry, let me do that in a different color. So we only have 6 electrons around the oxygen. We have 8 electrons around the nitrogen, and we have 8 electrons around the oxygen. So we don't have a valid Lewis dot structure yet. So what we're going to do is we're going to take these 2 electrons here and pull them in to form another double bond. And now, when we do that, we now have this oxygen has 8 electrons around it. This oxygen has 8 electrons around it. And this nitrogen has 8 electrons around it. Okay, so we now have a valid Lewis dot structure. Now let's use our formal charge calculation to figure out where the charge in this molecule resides. Okay, so since the oxygens are both the same, because it's on the same side, we're going to do one calculation for oxygen, and then we're going to do another calculation for nitrogen here. Okay, so let's go ahead and do the oxygen first. So the formal charge on oxygen is going to be equal to the number of valence electrons it had as a neutral atom. And we know that it's a group 6A, so it has 6 electrons that it brought to the bonding party here. Okay, so we need to subtract from that all of the electrons that are in lone pairs. So we have 1, 2, 3, 4 electrons that are in lone pairs. And it gets to use all of those as balancing its charge because it's not sharing those, and so it uses all that charge for itself. And then we have 4 electrons that were bonded. But remember, we only get to add half of those 4 electrons because they're shared with the nitrogen. And so by simple math, we end up with 4 plus 2 in the brackets here, minus 6, which means that this ends up being a total of 6. Minus 6 gives us a formal charge of 0. Okay, so there's a formal charge of 0 on both of these oxygens because they're the same. All right, so that means that the nitrogen must have that positive charge. Well, let's prove it by doing our formal charge calculation. So if we do that for nitrogen down here, formal charge is equal to nitrogen brought 5 electrons to it has 5 valence electrons in its neutral species because it's in that column 5A. So we're going to have 5, and we're going to subtract from that all of the lone pairs. Unfortunately, we have 0, so we have 0 lone pairs. Okay, plus 1/2 of the bonding electrons, right? And so we have 1, 2, 3, 4, 5, 6, 7, 8. Each of those lines is 2 electrons. That's 8 electrons right there. So that brings us 5 minus 4 is the number inside the bracket now, which is equal to plus 1. So that means the charge on this is on the nitrogen. It has a plus 1 charge, and both of the oxygens are neutral at 0 charge. Therefore, the molecule itself has a plus 1 charge. All right, questions on that?
No.
Okay, great. Okay, so what I'm gonna do one more real quick with a little bit less explanation, but I wanted to show a couple things on it because it is important to know when we have things that have charge and where the charge might be, because having charge on a species or a polar bond is where a lot of the chemistry happens, okay? So let's see, I'm gonna do this last one right here.
Can we try actually either F or I?
F or I. Okay.
Yeah.
All right, let's do this one right here then. Okay, F or I. Oh, that's a good one too, actually. All right, yeah. Okay, so in this, let's go ahead and start thinking about how we're going to do our Lewis dot structure on this. So the first thing we think about is that, okay, carbon usually has 4 bonds to it, so we're going to put carbon down first, right here, and it has 3 hydrogens in the formula here, so let's assume that's right and just put those 3 hydrogens there first. Okay, now we have an oxygen here, and so that's probably bonded to that. Now oxygen usually only bonds twice, so we're going to put one of the hydrogens there. But the way this formula is drawn is it makes us think there's another hydrogen here. Okay, so let's just count our electrons and make sure this is going to happen. So carbon brought 4 electrons to the party, so 1, 2, 3, 4. Each of these hydrogens brought 1. Okay, so that takes care of those electrons. These hydrogens each brought 1 electron to the bonding here. So oxygen, because it's in group 6A, has to have 6. So we have 1, 2, 3. And then we usually have a lone pair here, 4, 5. And then so, oh wait, hold it. We have 2, 2, 2, and a lone pair. So oxygen now has 8 electrons around it. Okay, so that's how many, so each of the atoms has exactly what it needs. We're not going to calculate the formal charge for hydrogen because we only have 2 electrons in each of those. And so what we're going to do is we're going to calculate the formal charge for carbon over here, and we're going to calculate the formal charge for oxygen over here, and we're going to see where that positive charge is, okay? So if we start with the carbon, okay, so the formal charge is equal to the valence electrons it has, which is 4, minus the lone pairs, and there are 0 lone pairs on carbon here, minus 1/2 of the bonded electrons. So we have 1, 2, 3, 4, 5, 6, 7, 8. So that's 8, which equals, the inside of this bracket is now 4. So we have 4 minus 4, which is equal to 0. So carbon has 0 formal charge. Okay, now let's figure out why oxygen has that formal charge of. All right, so let's go with the oxygen here. So oxygen is equal to, okay, so when we look at it, it's group 6, so it has 6 electrons here, and we're going to subtract from that all of its lone pairs, so that's 2 plus 1/2 of the bonded ones, 1, 2, 3, 4, 5, 6. So that's 6 right here. So half of 6 is 3 plus 2. So that's inside the brackets, which makes it 5. So we have 6 minus 5 is equal to plus 1. Okay, so that means the plus 1 has to be on this oxygen. Okay, so empirically we know our calculation is correct, and we did have a charge on our formula up here. But why? Why do we know that this is not there? Well, normally when we see oxygen bonded, we see it bonded to 2 things, and it has 2 lone pairs. So what's happened here is one of the electrons in its lone pair here is being satisfied by having that hydrogen bond to it. So basically that hydrogen is taking the place of one of those lone pair electrons. That way it's shared, and it's no longer 100% of the time on the oxygen, and that's why there's a positive charge on oxygen, because that electron has been moved to being inside that bond. Okay, all right, does that make sense?
Yes.
Okay, great. We have coming and going. Okay, all right, so you can go ahead and do this for some of the other ones. Again, do where you kind of put all your bonds around carbon and then figure out where all the lone pairs are, and then you should be able to calculate your formal charge fairly quickly. Okay. So let's kind of look at this, instead of doing a calculation, let's think about this kind of in a practical sense, okay? So we have a compound that is CO, carbon monoxide, okay? So let's figure out what a reasonable Lewis dot structure would look like for that, okay? So if we look for a reasonable Lewis dot structure here, we know carbon likes to bond 4 times, but it needs that total of 8 electrons around it. Oxygen usually bonds 2 times and has those lone pairs around it. So let's look at this one right here and figure out whether this one is an appropriate Lewis dot structure or not. So just by counting the number of electrons around each of these atoms, I think that we have 6 electrons near the carbon and 10 electrons around the oxygen. So I think that that is an inappropriate Lewis dot structure, because we have 6 electrons and 10 electrons. Both of those atoms want 8 electrons around them. So I don't think that's a really good way to do that. So let's look at this one right here. We have 1, 2, 3, 4, 5. Ooh, so this has 8 electrons around it, and oxygen has 8 electrons around it. So let's calculate formal charge on this and see what we see. We know that CO is a neutral species, so they either have to be equal and opposite charges or no charge at all. So let's do the calculation. Formal charge, carbon, for carbon, let's do carbon first. Okay, so we had 4 electrons is the valence number of electrons it has, minus, oh, it has 4 electrons that are in lone pairs, and then we're going to add to it 1/2 of the bonded electrons, which is 4, which makes 4 plus 2 inside the bracket, minus, which means the formal charge on carbon in this is -2. Ooh, That's kind of weird. Okay, well, let's see if it kind of balances out. Let's look at the formal charge on oxygen here. Okay, so oxygen, we know, is a group 6, so it had 6 valence electrons it brought in. Now we're going to subtract its non-bonding, its lone pairs here, which is 4 of them, plus 1/2 of the bonding electrons, which are 4, okay, which makes the inside of this bracket 6. So oxygen has a net charge of 0 because we have 6 minus 6 giving us 0. So this Lewis dot structure actually has a net charge of -2. So is it a valid Lewis dot structure for carbon monoxide?
No.
No, it's not, because this is a neutral molecule. This has a formal charge of -2, therefore it can't be a valid Lewis dot structure. Okay. So let's do these calculations again for some of the other Lewis dot structures, and we'll do them a little bit quicker because we're getting pretty good at doing this formal charge thing because we know where all the electrons are coming from. So if we do this carbon here, we have 4 valence electrons minus, let's see, 1, 2, 3, 4, 6 right there of non-bonded, plus 1/2 of 2 right here, gives us 4 minus 7, which is a formal charge of -3. Oh, that's probably not going to work out very well either, because we have a minus charge here. Well, let's calculate the oxygen, make sure that it has a charge. Maybe they're equal and opposite here. So we have oxygen here, and it brought 6 electrons to the party. And it has 6 lone pairs, 1, 2, 3, 4, 5, 6. And then we're going to add to it 1/2 of the shared electrons, which is 2. So that means it's going to have a formal charge of 6 minus 7, which is equal to -1. Okay, so this is -1. So that means this Lewis dot structure should have a charge of -4. So is it a valid Lewis dot structure for CO? The answer is no, because the formal charges are just wrong. We have two different negative formal charges. Okay, so if that can't be a good structure either because the math doesn't come out, let's go ahead and calculate it for this one right here, and maybe it's going to work out to be the best Lewis dot structure we have. Again, we'll do the calculation pretty quick. We got 4, carbon brings 4 valence electrons, and it's going to be subtracting it from the non-bonding, which is 2, plus 1/2 of the bonding, which is 6. Okay, so that's going to give us 6, 1/2 of it is 3, so we have 5 minus 4. So that means the charge on oxygen here is -1. Okay, so now let's do our calculation for our oxygen here. So our oxygen had 6 electrons. It has only 2 non-bonding electrons, plus 1/2 of 6 right here, giving us 3 plus 2 is equal to 5. So we have 6 minus 5 is equal to +1. Ooh, so we have a -1 on carbon and a +1 on oxygen. The +1 and -1 cancel each other out, giving us a neutral molecule. Okay, so even though we can draw a bunch of these Lewis dot structures, we know that the A, C, and D are not valid Lewis dot structures because the formal charges don't work out. Because the formal charges here are equal and opposite, it is our valid Lewis dot structure for carbon monoxide. Okay, so that would be our valid Lewis dot structure for carbon monoxide. And this breaks that rule I told you where we rarely have a lone pair on oxygen, but we do on carbon monoxide. All right, questions on that? Okay, So you can use this as a double check to make sure you've drawn something correctly and you have the right number of things appropriately around the different atoms. Okay, so that's how we draw the Lewis dot structures, and that's how we make sure they're correct. And now we're going to take that correct Lewis dot structure and figure out the shape of the molecule in three-dimensional space. Okay, everything we've drawn up to now has pretty much been two-dimensional, just in the plane of the plate. Now we're going to use what we call valence shell electron pair repulsion theory to tell us what it's going to look like in 3 dimensions. Okay. So as the name suggests, valence shell means only the electrons that are bonding do we care about, okay? So it's only those outside electrons that we bond with. And the idea is that electrons are negative, okay? So they actually want to repel themselves electrostatically, okay? So if you have 2 regions of area and space that have electrons in it, they're going to try to spread out as far apart from each other as possible. But remember, they're in orbitals. They're not just going to fly off anywhere. They have to stay in these orbitals to balance the charge of the nucleus. So they're tied to that atom. Okay. So what we end up with is the idea that if they're tied to that atom, but they're just going to want to spread out as much as possible. Okay. So I'm going to blow this up here. So if we have 4 regions of electron density around a central atom, that means we're going to have 4 places that we're going to have that are going to be negatively charged, and they're going to try to spread out as much as possible. Okay. Now, as it turns out, when you try to spread those things out in 3-dimensional space, the farthest you can get them apart is 109.5 degrees. Okay. So if all of those electron regions are exactly the same, they're going to be 109 degrees apart. Okay. And the proof we have for that comes in the fact that if we measured the angles in methane, where we have 4 electronic regions around that carbon atom, and they're equal because they each have a hydrogen in them, they're going to be 100. This gives us 109 degrees in between each of these species. Okay. So our hydrogens are also in what we call a tetrahedral structure. The molecule, the shape of the molecule is also tetrahedral. Okay, each of those hydrogens is 109 degrees apart. Okay, what if we had those same 4 electron regions, but we didn't bond to each of those electron regions? We actually only bonded to 3 of those electron regions. We see that in something like ammonia. Okay, so we still have that 4th area of electrons here. And so if we are looking at this as trying to be 109 degrees apart, but what that does is the 3 things that are bonded to it are now still in that little, pushed away from that 4th region, and we end up with something called pyramidal. Okay, imagine a 3-sided pyramid sitting on here, and that lone pair is up here. So electronically, we still have 4 spaces, but the molecular way, we're only bonded to 3 things, and that's why they're tilted down like this, because the electrons up here are forcing them down. Okay, so in the presence of water, okay, we have oxygen here, it only wants to bond twice, okay, but it still has these 2 big lone pairs up here. So electronically, it still has 4 regions of electrons in space. However, it only has 2 things bonded to it. So electronically, it's tetrahedral, that shape with 109 degrees apart, but molecularly, it's what we call bent, because this cloud is pushing against that, this cloud is pushing against that, these are pushing against each other, and these are pushing against each other, giving us, it's trying to be 109.5 degrees, but it's not quite. And we'll talk about that in the next slide. Okay, so if we only have 3 regions of electron density in a molecule, then those 3 would want to be spread out as far as possible. And the best way to do that is to actually kind of look like a propeller, where we have them all in the same plane. And so we form a 3-sided triangle here where the tips are the ends of those lone pairs, and that's as much as they can get apart. If you look at it in 3 dimensions, that's actually, making that just flat plane is the way to get them as far apart as possible. And what that ends up with being is that we end up with 120 degrees right here. So where do we see that? One of the simplest places we see that is in something like ethylene here, okay? Okay, so each of these is an area of electron density that spreads it out to approximately 120 degrees right here. And we see that, so we have those bonded together. So the molecular structure is actually planar because it's actually in the same plane as these as well. So when we look at this on edge in a couple of slides, you're going to see that it's actually flat in its own plane, okay? Likewise, if we bonded it to 2 other things, we see the same thing. It's this trigonal planar triangle thing here. Okay, now, so we had 4 electron regions. We have 3 electron regions, gives us trigonal planar. If we have only 2 electron, they are going to be 180 degrees apart. That's as far as you can get apart in 3-dimensional space. And we see that with something like carbon dioxide. And when we have a triple bond in between 2 carbons here, we see this to give us a linear structure. Okay, does that make sense? That if we have 4, it's going to spread out as far as possible, but the electronic structure is always tetrahedral, but the molecular structure depends on how many things are bonded to it. Okay, so let's take a little deeper into this methane, ammonia, and water. Now, if they were all the same and had all the same bonds on it, all of the angles between those different atoms would be the same. So we see that in methane, which is CH4, right here, we see they're all equally the same, okay? So the hydrogen over here, those electrons are repelling the other electrons from the next hydrogen over the same amount as the other 2 other hydrogens. So they are perfectly balanced at 109 degrees, that perfect structure, okay? However, when we have a lone pair up here, and we have these bonds here, this is actually larger, takes up a little more space, and actually pushes away these things a little bit more. So what we end up with is these are actually 107 degrees apart. This is actually taking up more space, and so the angle in there is actually not 107, it's slightly larger. But these are bigger than this hydrogen here, and therefore they're pushed down more, and the angle gets smaller for those bonds that are available to it, okay? We see this happen one more time in water because the big lone pair here and the big lone pair here are forcing the 2 smaller regions, which is where the hydrogens are. They're bigger, and so they force them a little bit. So the actual angle between the 2 hydrogens is even smaller at 104.5. Okay, we don't need to know the exact angle other than the tetrahedral is always this 109.5 is the ideal number, but the lone pairs are bigger than the hydrogens in this case, and therefore that changes the angle. Okay, so let's go to that 3 regions of space. Okay, so we have 3 regions of space and we expect them to be 120 degrees apart. However, if you have more electron density or a larger atom, that's going to take it out of that ideal 120 degrees. Okay, so in the case of this compound here, formaldehyde, where we have hydrogen, which is kind of small, and oxygen, which is much bigger, what we see is we get a bigger angle. This is forcing the angle out more than that 120 ideal degree structure. And so what we see is the hydrogens are actually squeezed together a little bit by about 3.5 degrees. Okay, so the size of the atom in the structure can control can vary from the ideal 120 degrees. So the bigger the atom gets, the more it's going to force the smaller atoms close together. Now, again, I said this is planar, so we have this, you know, this trigonal planar thing. If we look on the side here, all 4 atoms are in the same plane. Okay, so that shows us that it's the trigonal because it has 3 things bonded to it, and planar. Okay. Now with ethylene, which is, we're going to add a little more complexity because we're adding another side here, we're going to see that same thing. This carbon is bigger than the hydrogens here. Therefore, our angle is slightly larger than 120. The angle between the hydrogens is slightly less than 120, but that planarity continues across to the other carbon. So this carbon here was trigonal planar, but the other carbon is also trigonal planar, and the entire molecule stays planar. So if we look on the edge here, this is the 3 bonds for the first one, and then this is the 3 bonds for the second one, and they all stay planar. Okay, now when we extend that up to the linears, we see that in something like carbon dioxide, we only have 1 region of electron density here and 1 region of electron density here, giving us this linear structure. And if we look at on the end, all 3 atoms are in a row. We can extend that to even more longer ones like this. This is acetylene, this is 4 atoms. So this is 1 region and this is the second region. So we're gonna have 180 degrees apart here. This is 1 region and this is 1 region. These are gonna be 180 degrees apart here. So what that makes it is the entire molecule, all 4 atoms line up, and we have a linear molecule. So this should say linear, not planar. Okay, so how can we use this to our advantage? Well, looking at this valence shell electron repulsion is going to help us decide what the shapes of different molecules are in 3 dimensions. Okay, so let's practice with that a little bit. Look at these Lewis dot structures that we're gonna do 2 or 3 of these, and we're gonna try to figure out what the shapes are. Okay, let's start with something simple first. Let's start with this one right. Whoa, don't go away. Let's start with this one right here. And the way we would draw our Lewis dot structure is, of course, we put the nitrogen in the middle because it's going to bond the most. And we're going to have 4 hydrogens on it. And we know, because we calculated the formal charge, that there's a plus charge on this nitrogen here. Okay, so what shape is this molecule? Okay, we have 4 regions of electron density. Okay, so that means our electrons are going to be tetrahedral. But we also have 4 things bonded to it. So that means our molecular shape of this ion is going to be tetrahedral. Okay, now how do we draw that on flat paper? Okay, when we draw that on flat paper, what we're going to do is we're going to take 3 of the atoms and put them in the plane of the paper. And we do that by saying nitrogen and hydrogen and hydrogen. Okay, so all 3 of these atoms are in the plane of the paper. Now, to make it tetrahedral, one of them has to go behind the paper and one of them has to come out of the paper. And we do that by saying a dashed line to this hydrogen tells us it's going behind the paper. To give it 3-dimensionality, it's going behind. And we're going to have to draw another one out in front of the paper, right here. And we do that with this solid wedge. Okay, so now we've taken our 2-dimensional Lewis dot structure and converted it into something that has 3-dimensional space. Well, let's not forget our positive charge here. Okay, so that is how we take our valid Lewis dot structure and convert it into a physical molecular structure in 3 dimensions. Okay, does that make sense so far? Yeah. Okay, all right, let's do another one. Let's do this one. Let's see, let's do this one next. Okay, no, come here. And I'm gonna erase this so we have a little more room. So let's draw our valid Lewis dot structure first. We've had a lot of practice with that, so I'm gonna do it a little bit fast. So we have a carbon with a hydrogen on it and a carbon with 3 hydrogens on it. And then a double bond because it shows us you have one, and then a hydrogen here and a hydrogen here. Okay, so right away we have 2 different molecular geometries around the different carbons, right? This one right here, we expect to be tetrahedral because it has 4 things bonded to it. Okay, so we could probably just start with something like adding one of these coming out of the plane and one of them going into the plane here to show that it has 3-dimensionality. But let's talk about these 2 other carbons. These 2 other carbons have 3 things bonded to it, okay, which means they're going to be trigonal planar, okay, because you have 3 things that has to be in that trigonal planar molecular composition. So one way we could redraw this is to show that this part is planar by drawing it such that we show this hydrogen is going back out here. This hydrogen is coming out at us right here. This hydrogen is going back out here. And this carbon is coming out at us and has 2 hydrogens on it. Actually, that carbon is, this carbon is behind this carbon, so we're going to draw it that way instead. And that takes our last hydrogen sticking out here. Okay, so what we see is that this is going back toward that other carbon, but this structure right here, this half of the structure here, is planar. It's a flat plane. Okay, it's that trigonal planar. This carbon right here is tetrahedral, or has those 4 areas of bonding. All right, questions? We're good?
I'm still like trying to understand how did you know which ones go like in the back and which ones in the front?
Okay, let's do a simpler version of that, and let's take just half of this molecule here. Let's do CH2O. Okay, so it's going to be a little bit simpler, but it's going to help us demonstrate exactly that premise, okay? So let's just draw that simple one there, and it actually has a name. It's called formaldehyde. But what we're going to see here is it's all about perspective, okay? So let's again do this one right here. And so we have a Lewis dot structure. If we draw it, it's going to look like this right here. So this is what the Lewis dot structure would look like flat, okay? So when we look at this, okay, the carbon is probably going to be trigonal planar because it's got 3 things bonded to it. Okay. So what we're going to do is we're going to translate what this is, and what we're going to do is we're going to rotate it around this way and try to look at it as if it was flat, okay? So to do that, what we'll see here is that we're going to put the carbon and the oxygen in that one plane. Now, if we do that, that means one of these hydrogens has to be behind the carbon and oxygen, and one of these hydrogens has to be in front of the carbon and oxygen. So we would show one of the hydrogens going back and one of the hydrogens going forward. Okay. So this is what I was trying to draw before, where I was showing you that this hydrogen was out away from that carbon in this carbon. Does this make sense?
Yeah, that was easier.
Okay, so the difference is when we added that new tetrahedral carbon, right, we had to have, one of them had to go forward and one of them had to go back, okay? But we'd already have this solid wedge. This solid wedge was representing it coming from this carbon, and the dashed wedge I drew is from this carbon to that carbon. So it's all about the perspective of where it would be. So if I redrew this to be with a hydrogen up here, a carbon here, and a hydrogen here, we would have to draw our last one out here. So that could be down or somewhere else. Okay, does that make sense now?
Yeah, I think it does. Yeah.
It's just that you have to think about your perspective of which carbon you're trying to make the forward and the reverse. So that's what it would look like with just that simple one. Okay, so you have a couple different examples that you can do on your own, and then we can come back and see how those work out for you. And so, but the key here is, 4 bonds, try to make it tetrahedral. 3 bonds, try to make it trigonal planar. 2 bonds, try to make it linear. Okay? Okay. So let's take this a little bit one step further and look at this really big molecule here. Okay, and we're going to do this in chapter 9, and we're going to show you something very interesting about this molecule. Okay, so let's take what we know about each individual carbon and expand upon it, right? So what we know is that, let's start with this one right here. This carbon right here, it has 3 things bonded to it, which means this makes a plane between those 3 atoms that it's bonded to, okay? So we get that, right? Those 3 bonds are gonna form that trigonal plane, okay? So now let's look at this carbon here. We saw in ethylene that when we had them 2 trigonal planars next to each other, they made one plane between them, right? So if we look at this plane of this structure here, this red plane and the blue plane are in the same plane together, okay? Just because we have 3 things bonded to something next to 3 things bonded, okay? Let's look at this carbon now. We're gonna have another plane of those 3 atoms. And the red plane and the blue plane and the yellow plane are all within the same plane because you have the 2 planes next to each other, the red and the yellow are flat with each other. The red and the blue are flat with each other. Okay, so let's do this carbon here. We're gonna see the same thing. This is gonna be a nice flat plane and it's gonna be all flat again. And then let's do something in the purple range here. We're gonna have this one and it's gonna do the same thing here. And that means our last one here is also going to be planar, okay? So what that means is that if we were to draw this benzene ring on its side, we would see a carbon, a carbon, a carbon, a carbon, and hydrogens would be sticking out like this. So the entire thing would be a flat plane. All 6 carbons are in a flat plane. All 6 hydrogens are in a flat plane because all of those trigonal planes come together to form a flat system across the entire thing. So our VSEPR theory suggests that this benzene molecule should be planar. And I'm telling you it is, and we're gonna get to that in chapter 9. All right, do you see how by adding each of the things we know together, we can get the entire molecule assigned? Okay. Now that being said, if we think of each of these being trigonal planar, what does that make each of these angles here?
109 degrees.
That's the tetrahedral structure is 109 degrees.
Oh, so 120 then.
Would be 120, right? So each of these is 120, and so that all of the bonds everywhere in benzene are 120 degrees. They're all trigonal planar, and it gives us that flat benzene shape. Okay, let's see. 5:32, so we got 15 minutes, perfect. We're right on schedule. Okay, so now that we have an idea about how those electron regions give us the shape of the molecules, let's talk about how the formal charge on the different parts of the atom give us polarity in our bonds. Okay, now remember, when we looked at these atoms, okay, some atoms had a higher electronegativity than others. Okay, so the closer you got to fluorine on the periodic table, the more it wants electrons. Okay, which means even if you have a bond between two atoms here, if this one wants electrons more, it's going to pull some of that electron density, giving us a partially negative sign. Okay, now what that means is that that bond is polar because this atom is more electronegative than this atom. Okay, now that's for an individual bond. When we talk about the polarity of a molecule, we have to know where each of those bonds is pointing to and see if they add together or if they cancel out. So in the case of this molecule here, carbon dioxide, if we just compared the electronegativity of oxygen and carbon, we would see that the oxygen is more electronegative, okay? It's closer to fluorine on the periodic table, okay? Which means it's gonna pull some of that electron density away from the carbon and give more electron density to the oxygen, okay? So if we only had the carbon and the oxygen, we would have a polar molecule. But we have another oxygen, and we have that oxygen, and we know that this is a linear molecule, so it's 180 degrees apart, okay? So now we have this polar bond is pulling in this direction here. So we have an equal and opposite charge pulling this apart, okay? So the carbon-oxygen bond is polar, but the molecule itself is nonpolar, okay, because they're equal and opposite. So this is where that idea of a polar or nonpolar bond gets added to that, the valence shell electron repulsion theory on the molecular shape. We're going to add those two things together to give us whether or not the entire molecule is polar or nonpolar. Okay, do we see how that when we have this, that they're equal and opposite each other, and because they're pulling 180 degrees apart, it's like, zero, when we have a non-polar molecule. Okay? Let's see if that applies to other molecular shapes. Okay, so let's take a look at water. That's a really common molecule we use a lot. And what we know is by our valence shell theory, we're going to get this bent molecule, okay? Because these lone pairs are going to take up space. These lone pairs are taking up space and giving us a bent molecule, okay? So in general, we would expect these to be about 109 degrees apart, or maybe a little less because of those there, so that they're not equal or opposite to each other. They're actually kind of facing kind of in the same direction toward the oxygen molecule here. So if we think about what is more electronegative or electropositive, oxygen has a higher electronegativity, so it's going to pull electron density away from the hydrogens. Okay, so this bond is going to be polar in that direction, and this bond is going to be polar in that direction. Okay, so they're both pointing up. Okay, so these are not equal and opposite charges as if it was linear right here, which means that we now have a net charge is up, because the ones going toward it cancel out, but the ones going up add together. And therefore, in this tetrahedral-like molecule, because we have polar bonds, and we have two polar bonds going almost in the same direction, we now have a polar molecule. So the molecule itself is polar in this direction here. This is the electropositive side of the molecule, and this is the electronegative side of the molecule, usually denoted with the red side versus the blue side. Okay, do we see here that we have to add what we know about polar bonds to the molecular structure to determine whether a compound is polar or not? Okay. All right, let's take it with another structure here. All right, let's go to our ammonia. Okay, if we look at ammonia, we have, it's a tetrahedral structure. We have 4 regions of electron space, but we only have 3 bonds to the nitrogen here. And nitrogen is more electronegative than hydrogen, so it's going to pull electron density from the hydrogen to the nitrogen, to the nitrogen, to the nitrogen. They're all pulling into the middle here, but we still have a net polarity where those electrons are. We have more electron density up here because they're going in that direction than we have for the hydrogens. So we have a net polar molecule because those three polar bonds are all end up going a little bit in the same direction, and we have a polar molecule. Okay, all right. So that means we can do this with any and every molecule that we have. All we have to do is figure out where those electron regions are and which direction the polar bonds are pulling. So if we had methane, where we replaced this chlorine here with a hydrogen, we would have a hydrogen. The carbon is going to be a little more electronegative, so we're going to have hydrogen here, hydrogen here, hydrogen here, and hydrogen here, and they're all going to cancel out. So in methane, because all of these polar bonds cancel out, it has a net non-polar molecule. Okay. However, if we replace one of those with a chlorine, chlorine is more electronegative than carbon. Therefore, it's going to have this pull in that direction, and chloromethane is going to be polar. Okay. So if we look at this trigonal planar molecule, now we can see that it works well in trigonal planar molecules as well, because we have the oxygen on this side of the molecule is different than the hydrogens on these side of the molecules. So we have a net dipole, we have a net pull of electrons toward the oxygen because it's more electronegative, and therefore the entire molecule, even though it's trigonal planar, is still a polar molecule. Okay, so in the case of our linear ones, because we're having equal and opposites pulling against each other, we end up with a non-polar molecule. Okay, questions about that? Okay, great, great. So the color coding here really kind of helps to kind of help you figure out what happened. Okay, I'm going to save this last section for next time because it's actually about 5 or 6 different slides. We don't have time for that. All right, any questions about polarity or thinking about how these regions of electrons, and then by bonding things to it, we go from the tetrahedral electronic state to different molecular states based on how many things are bonded to that central atom? No? Okay.
No.
Great, great. So, all right. So what I'm going to do is I'm going to go ahead and stop recording right now, and I'll post this in a little bit. It takes about 30 minutes to process, so it takes a little while. I'm going to, let's see, there it is. Stop.